So my name is Nate Abele, and this is Un-dux your front end, or the unreasonable effectiveness of data. So this is me. It's a photo of me in case you weren't sure what I look like. You may know me from the internet associated with some of these fine projects. I was the lead developer of the Angular UI router framework for about 1.5 years. How many people have used UI router? All right, a few of you. Nice, my people. I am an architect at a fintech startup called Advisor Innovation Labs, and they have graciously sponsored my ability to be here today. So let's talk about concepts. As programmers, we're all familiar with and comfortable with the ideas of concepts and tangible representations of those concepts, or to put it another way, abstractions and implementations, or Plato's cave or whatever. So let's talk about the concept of cow. This is a cow. Now in the space of the concept of cow, there are many possible implementations. This is one implementation of cow. This is another very different implementation of cow. You could consider them opposite ends of the cow spectrum of implementations. So again, cow. One concept, many different possible implementations. Keep this in mind for later. We're going to come back to it. Let's talk about state. Not that kind of state, but let's say you have a React application. If you actually have a React application, that's great. Then you don't have to imagine. So you have this application, you grow it, and these components are getting bigger and bigger, and they all have these little pieces of state that they're keeping track of, and that state is changing constantly all the time in response to user interactivity, in response to network traffic, in response to time. Now, the computer is great at keeping track of all of these things changing continuously all the time. As a human, I'm not so good. So this brings us to Redux. Redux is the de facto solution for managing state in React. So Redux provides a single value store to pull all of those pieces of state out of your components and into one place. It allows you to express changes to that data as simple values. And it doesn't have very many opinions on how you use it or how you structure your application. So to get started with a real-world Redux application, first you have to install the universe. And then you have to figure out how to get all of these pieces of infrastructure to talk to one another. And then you have to figure out what a thunk is. And then you have to figure out the internal mechanics of Redux, which it forces on you when you are implementing your application in it. And just in these few lines of code, there's all kinds of opportunity to mess things up and get things wrong. It imposes certain things that it needs on you. For example, all of your data that represents your changes, even though that's specific to your application, you have to have this thing called type. And then eventually, your application starts to look like this, and this is actually recommended. An important thing to note here is that all of these pieces, like selectors and reducers and services, they don't have anything to do with the semantics of your application. They're all just the mechanics. They're describing mechanics of how data and changes move through your application. In other words, reducer is a stupid name. So it was surprising to me to learn that Redux was actually inspired by an entirely different language called Elm. So Elm is a language that compiles to JavaScript and is a pure functional and statically typed. And in contrast to Redux, Elm has a refreshingly simple architecture that looks like this. And it only has one install to get up and running. You only need to install Elm itself, and because Elm provides the right abstractions as opposed to the complicated diagram that we saw before, you can write an Elm application and I can write an Elm application, and our code ends up looking about the same. And not because somebody told us to or because we coordinated on that, but because Elm provides such good abstractions, applications just end up looking the same across different people. It just sort of happens. So after using Elm for about 6 months, I was hired by AI Labs to architect their platform. And they were using Redux on the front end. And I looked at the code and I was like, what is this? I'm not doing this. After 6 months of Elm, I was just, kind of like, forget it. So I decided to port pieces of the Elm architecture to JavaScript, which became the project called CASIUM. So the code for an example piece of an application written in CASIUM looks like this. If you're familiar with the smart and dumb components pattern from React, this should be a very familiar idea. All we're doing is giving a more idiomatic way to write smart components, which is what this is. So this renders out to something that looks like this. It's very simple. And we'll just go through it one piece at a time. And as we go through it, you'll notice that if you've ever used Redux before, we have all of the same pieces here that you would find in Redux, but by presenting them in a different way, we're able to get a much cleaner code. So at the top here, we have this init thing, which just returns our initial model where our application starts out. The next section here is called update. This is where the magic happens. So you can see up at the top there, I'm making a class called increment, and that just extends message. So it's just a normal ES6 class. And then in the update section, I'm pairing that message constructor to a little update function that just takes the current model and returns a new one. That's all it does. And then down at the bottom here in the view, I have this special emit function that allows me to take a message and bind it to the container to create an event handler. And so I can assign that event handler to my view code, and that's how changes are propagated through the application. So same with decrement. We just define the message, bind it to an updater, and assign it to the view with an emit call. So again, the important thing to note here is that updaters are just functions that take a model and return a model. We're not concerned with dispatching the action or making sure that everything is in the right place like Redux does. We're just transforming the model from one state to another depending on what kind of message we get. So here, all we're doing is implementing implementing a model with a count key. It's just a number, no big deal. It's a very simple example purposely because it's a talk. But I'd like to introduce a functional programming library that pairs really well with CASIUM to see how even this simple example can be simplified even more. So that library is called RAMDAJS. Raise your hand if you've used underscore or Lodash or anything like that. All right, so most of you. Underscore and Lodash advertise themselves as functional programming libraries. Those are lies. In the US, we call that fake news. So they're not functional programming libraries. They may supply a library of functions to use. However, Ramda is fundamentally different in the way that it's designed, such that it actually allows you to build up applications from small functions to larger, more complex functions, and we'll see how that works now. So Ramda has a function called evolve that takes 2 parameters. The second one is an object that you want to transform, and the first one is an object with the same shape as the object that you want to transform, but the values are functions that are going to act on each one of the values that you want to transform. Hopefully that makes sense. So here I'm only giving it one of those functions, the first one that transforms the key. So because I'm only passing one function, it's actually going to return a new function that is going to expect the value that I want to transform. For those of you who aren't familiar with functional programming, that's called currying. Which is beyond the scope of this talk. Just take my word for it, it works. So we've shortened up the code a little bit, but there's still a lot of duplication going on here. And the actual operation that we care about is getting lost in all this noise and all this boilerplate. So fortunately, Ramda comes to our rescue again with increment and decrement functions that I can replace those two functions I'm defining manually with. So now, not only have we cleaned up the updaters, but this code succinctly describes exactly what it does. It evolves a count key by either incrementing or decrementing it, and I can just read it and understand exactly what it does because it says what it does. This is one of the benefits of functional programming, is that you can write code that describes exactly what it does. It's very terse and very, it's both terse and easily understandable at the same time. So let's take a look at a slightly more complicated example. This is a very simple login form. So I have an update form message that's going to update either one of these two fields. One of the things to note is that the emit syntax I'm using here is slightly different. Instead of just passing a message, I'm passing a message along with some extra data that I want to come back into update. So I give it a key of either email or password, and that determines what key gets updated. Now then, to actually log in, we can implement the onSubmit with just another message. But to actually do the post, I don't fire off an HTTP request. All I do is create a new message called http.post, and I give it the parameters that I want to submit. And the architecture, the underlying architecture has an effects handler which translates this to an actual HTTP call for me. And we'll see why that's important later. But the other thing to note is I'm giving it two messages here, sign in success and sign in error. So just like binding to the messages to the view, these bind to the responses of this, what's called a command message. And again, command messages are used anytime that you want to do a side effect, that you want to do something that modifies something outside of just the model. So then sign in success and sign in error are implemented as just any other type of message, although these messages take data. So our update function, instead of just taking the model, is now taking the model and the data that goes along with that message. And then we can handle those however we see fit, either redirect the user or show an error, whatever the case. Now, suppose we've gotten a feature request to implement OAuth. Now, this post command is already pretty noisy. And if we need to implement OAuth, it's going to get a lot noisier. So instead, we can implement a custom command message. And again, since message constructors are just normal ES6 classes, I can extend the built-in post and then take this and encapsulate all of my message logic separated from the container. And testing this is extremely easy because it's just a class that takes two values in its constructor and builds up an HTTP request. So I'm able to isolate this part of my business logic away and encapsulate it in a very easily testable way. And if I want to clean it up even more, I can pull in the sign in success and sign in error and put them down here so that our container goes from this to this. So the whole request happens in one line, and it's very clear and easy to see exactly what sign and submit is doing. It's modifying the value of loaded so that we can show status in the UI, and then it's firing off the command. So this is good, but we can actually do a little bit better. CASIUM has an SEQ function which allows us to sequence multiple updaters together. So we can take these two logically separate operations and split them up. Now this is obviously more verbose, it's more boilerplate, but splitting them up allows us to have an intermediate step that we can, from which we can take the next step of refactoring to make everything a little bit more clear. And that final step of the refactoring looks like this. There's a helper called replace and a helper called commands. Replace just flips some values in your model. So we're just saying, okay, we want to set loading to true, so just replace that value. And then the commands helper just gives us a little bit nicer syntax that takes a command constructor like sign in. And then this second value here is another Lambda function called pick that's going to take the model and just pick out the email and the password fields and pass them to the sign-in constructor. So here we have a succinct description of what exactly it's doing. We have independent functions that can be extracted and reused across multiple containers. And the whole thing was built using function composition. I didn't have to write a single function manually. I just built it up from other functions. So the question that comes now is, why go to all the trouble? Programming in this style and managing all your changes through messages seems unnecessarily difficult, so what's the point? What's the payoff? Well, for one thing, testing. So imagine you are going to write a test for the plus operator. Well, of course, the first thing you have to do is mock out the plus operator factory, and then you have to stub out the plus operator service. No, you don't have to do any of that. You just take two values, call plus with them, and assert that the output is what you expect. So when you're working directly with data, testing your application becomes trivially simple. There's no mocks, no stubs. It's just values in and values out. And writing your application this way and having an application architecture that supports you writing this way allows you to do that. So for our apps at work, we don't have any mocks or stubs. Testing is trivial. But there's a more important principle at work here, and that is the principle of guarantees. So guarantees are properties that an abstraction has that allow us to build up more complicated things on top of it. Promises are a really good example of this. Raise your hand if you deal with promises at work. Unless you're not a front-end programmer, that should be pretty much every hand. So promises have certain guarantees they provide us that allow us to build complicated systems on top of them. For example, they're immutable. You fire them off and they resolve or reject exactly once and never change. Promises auto-unwrap. You can return a promise from a promise and the outer one resolves with the value of the inner one. And they're chainable. And just these few simple guarantees allow us to write very complex async systems just by composing them together. So guarantees are really important. But what happens when you decide to compromise on a guarantee? Let's say you're using Redux and it doesn't really have that many opinions, and it says, if you want to store a little bit of state in some of your components, you know what, that's fine. A little bit of local state is fine. Well, when you compromise on a guarantee, it's not a guarantee anymore. Instead, what you have is a probably. We have probablys all around us as programmers that we're forced to deal with every day. And I think we each have one that we probably hate the most. Some examples are DNS. Does the domain name resolve correctly everywhere in the world? Probably. Email. Do messages arrive in our users' inboxes correctly every time? Probably. What about caching? Is the page loading the correct version of the script? Probably. So that's really annoying and frustrating, but what if the systems that we depended on to do our work every day worked this way? What if we lost the basic guarantees for, let's say, a git checkout? If you were working with a colleague and they said, hey, check out this commit hash, you'll probably get the same source tree that I have. Or what if our unit tests only probably passed? This would be totally unacceptable. And yet, every time we struggle to debug a complex asynchronous process or get a report from a production system of an error that we have no idea how to reproduce, every single time that happens, we are living in the world of probably, the world of maybe, the world of, I don't understand, this should never happen. So I would like to introduce you to a different world. And I'll introduce you to that world as soon as I resize this window. Well, that's close enough. So this is one screen of the application that I work on at work. As you can see, it's a login form. And as I type here, you'll notice that things are changing. I've got these messages here, and those messages are telling me what is happening in the application. As I click through, you can see that I get these changes in this nice little highlighted diff that's telling me exactly what my application is doing. And I can see the full model that represents the application in that particular state. So, and because the view is a pure function over the model, for any given model, I should see exactly the same thing on the screen every single time. And representing applications this way allows us to do things like generate unit tests. So I can say for any given message, if it does what I expect, I can just snapshot the unit test and put it into my test suite. But we can go beyond that. We can, let's say, time travel, where I can actually just step back through my sequence of messages and see what my application looked like at any given point in time. And finally, I can export a message log of everything that just happened. So I can go through a user flow in my application and then just take a snapshot of that log. And it looks like this. So this is the JSON of everything that I just did. So what we can do even more interesting things than that. For example, let's say I have a different device and I want to actually mirror one device from another. This did work. Let's see here. Oh, I'm reloading, sorry. You'll have to take my word that this worked 20 minutes ago. Oh, come on. Yeah, it's fine. Still loading. But anyway, the idea, what you were supposed to have seen is me typing on here and it showing up on the screen there. So, and it definitely works. I'll set it up later in the speaker's corner. Anyway. So what did we just see? We saw a diff view of changes, color diff, just like we see in our source editor, of exactly what is changing for every single message. We saw generated unit tests because the system is keeping track of everything that's changing every single time, every single input. We saw time travel. We can move back and forward in time and see our app in different states, which is especially useful for a lot of complicated asynchronous things happening quickly. And we're able to export all of that data as JSON. And finally, what we didn't see was WebSockets magic. Just imagine it in your mind. So what are some of the implications of this? For one thing, between the time travel and the thing that you imagined in your mind of the iPad and the screen, we saw, or variously didn't see, the state of our application crossing different boundaries, either over the network or time. And that and we can take that idea and extend it out further. If we can move data from one device to another, well, it's just as easy to take data from one device to another as it is to take data from one device to 5 or 10. So if you have to test across multiple, let's say, mobile devices for your application, well, you can trivially build a device farm just off of designing your application this way and hooking all your devices up to the same network. You can reproduce errors in production with a full audit trail of exactly what the user's state was when they encountered the error and every single step they took to get there. Extending from that, you can store those logs and actually not only watch user behavior in real time, but play back sessions from any user at any point. Also, you have this nice isolation between your front end and all of the other services that your application connects to. So you saw in the example here, let's just do this quickly. And I'm going to do a wrong password just to quicken this. So here, I have this sign-in message that fully encapsulates the request and sign-in error, which fully encapsulates the response. So what that means is I can not only test the full front end of my application, fully isolated from any services that it talks to, but by exporting that message log, I actually have the ability to automatically generate tests for all of my APIs. Because I'm capturing both the requests and the responses, so I can say, oh, here are all the API requests that happen for this user flow. Here's what they should do. And I get that for free. So we have one final implication, at least that I can think of. I'm sure there are many more. That lets us think differently about how software behavior changes over time. And that's diff analysis. So we can take the diffs that we saw in the browser tool and extend that idea into something that allows us to explore how we verify the correctness of our software beyond unit testing. So I can go through a whole user flow for login, for sign up, for any particular feature, and export a message log. And then all I have to do the next time that I'm working on that feature to make sure my tests pass, I don't even have to write any tests. I can just run it again and make sure that the message logs are the same. So what if instead of unit tests, we just use the replay log to verify that everything still worked as expected? We can fully validate that in a fully automated way. But we can take that idea further. Most of us generate our applications using something like this, and that produces a build file with a particular hash. We can think about that hash similarly to how we think about a git commit hash. It's a unique identifier that represents that version of our application. So by combining this with a snapshot of the model from our application, we can actually reproduce any UI across any state, across any version of our application. So then that allows us to actually take this concept of diffs and understand how our software is evolving over time as a mapping of data. And this opens up all kinds of opportunities to verify the correctness of how our software is evolving and still maintain that it's doing what we expect. See, the problem with unit testing is that for any sufficiently complicated system, the number of possible states that it could be in outnumbers the number of atoms in the universe. So unit testing is basically saying, okay, this one atom is definitely good, but we have no idea about all the others. So the place that I'm trying to get to is where we can say not only that the software does what I expect, but that it also doesn't do what I don't expect. And this is a way that moves us closer to that. So we can start to produce better, more reliable software and ultimately better experiences for our users. And hopefully less work for ourselves. So if you want to try it out, you can clone both the framework and the dev tools from GitHub, or check out CASIUM.io. For more information. Thank you. And we have a few minutes for questions. Is there right here? Somebody? Oh, sorry, you have a mic.
Yeah?
Yes, go ahead.
It seems a very cool thing, really, but the main problem for such new frameworks is about to maintain, because we all know that in time, if any other people come to the project and see some not maintainable the project, it will be the bad idea. So what are you planning to do with sharing this to be to involve as much as possible other guys, except today?
So, besides today, because today is definitely one of the answers. No, I think, and that's a good question. So you're basically asking, how do you know that this isn't going to go away in 2 weeks? Well, for one thing, I use it at work, and we are an extremely well-capitalized fintech startup, so there will always definitely be at least one maintainer. But no, I think beyond that, to me, it's really about creating the best possible developer experience for writing applications, for writing front-end applications in JavaScript. So the dev tools that you saw, that's like an alpha version. We have so many more ideas that we're developing for how to allow you to work with software in a much more fluid way, while eliminating a lot of the boilerplate and the grunt work of things that we have to do, like writing unit tests. So the more that we can do that, and the more that we can sort of evangelize this philosophy and write more tools around this philosophy, which we're already doing, I think it's easily going to overtake Redux in popularity. Just because I don't think Redux provides a very good experience, and I think we can win in all the areas where Redux is winning right now.
Thanks for the presentation, and especially for UI router. It was like one of the best libraries I've ever used, and also very nice code style that I love it. But why use classes for functional programming? Like, I saw you like use it pretty much frequently. Why use classes and inheritance?
So that's a great question. Why use classes and inheritance in functional programming? And first of all, thank you. That was very gracious about UI Router. I give the same answer about all my open source projects. You're welcome, and I'm sorry. To be fair, though, this is the one that I'm probably least sorry about, because I think it's the best idea that I've had so far, because most of them weren't even my ideas. So to answer your question, the classes are just a mechanism for storing the data. So all the objects that you saw instantiated are fully immutable. And functional programming isn't really about not using classes necessarily. It's about how you structure your application. So you have values like numbers or strings. Like obviously those are immutable just by virtue of being literals, right? So we're really just using these message classes as containers for data. They're really more like a data type than how you would think about a class, because they don't have any methods. They're just carrying some data around, and they give you something to match on. Does that answer your question?
Yeah, just for typing. You use it for more
yeah, so basically for typing.
That makes sense.
Thank you for the presentation too. I wanted to ask you about the global state. Yeah, by looking on your examples, I saw the container function, yeah, which produced some kind of component, yeah, and it looked like Mobix component, yeah. Each component has own state, yeah. So how do you handle the global state of your application? Something like RAMDAJS approach. Do we have linked from any component to global store or something like that?
That's a good question. So let me see if I can sort of distill that down. So how is state managed at the global level? And if I have a component that's sort of deeply nested in the state tree, does it have access to the top level state? So great question. That gets into a whole bunch of topics that are basically about, okay, we just went through how to write a very basic application. This is like, how do you structure a large application? And so I'll just go through like really quick some of the concepts, and we can talk about the rest of them after in the speaker's corner. So first of all, when you have a message, that message has to be handled. Like there's runtime checks that guarantee that you can't render a view that has that emits a message that isn't handled. But where you handle that message is up to you. So I can have a message that's down here, and that message has to be caught somewhere between the root and there. So I can handle it at the root, or I can handle it somewhere in the middle, or I can handle it where it's being emitted. So that's basically how we control who has write access to what. And then as far as controlling read access, there's another concept called delegation, where I have a top-level component and that has a key, and I can delegate that key and everything inside of it to another component. And that component can make any changes to the thing that it is delegated to it. And so there are a couple of other mechanisms that allow you to control the behavior. But yeah, you can't just write from anywhere. It's all very controlled and very well isolated with the way the message system works.
Hey.
Okay, who has the microphone? Okay, this will be the last question, and we will move to Speaker's Corner, okay?
Great.
Thanks.
Okay, thank you for the speech and for the framework. It looks like functional and sexy, like Elmi's. So how do you think, what is the entry level for using your framework? Like Redux is pretty easy but not obvious. What is the entry level for the developers for your framework?
So that's a good question. So it's like, how does the learning curve compare to Redux? Is that okay? I think it's hard to say. I would like to think that this is simpler. So the learning curve here is learning to program in functional style, but the mechanic is very simple. It's like you have functions that take values in and return a value. Like, if you're a programmer, you can understand that. As far as more complicated refactorings and stuff like that, yes, you have to learn how to program in functional style, which partially means unlearning some things about object-oriented style. But I think this is a simpler and shallower learning curve than installing a whole bunch of packages and trying to figure out how to wire them up to talk to each other. So it's a different set of things that you have to learn, but I think my set of things is ultimately simpler and more effective in the long term in learning to be a better programmer. So I'm willing to evangelize in order to help other people with that, if that makes sense.